So here we're going to answer some questions, do some calculations involving some of the characteristics of waves. Remember, those are the things we talked about in class: wavelength, amplitude, period, frequency, phase shift. Wave speed we're going to save for the next video. So first of all, frequency. If a speaker vibrates 200 times in 1 minute, what is its frequency? Well, remember, frequency is just the number of cycles per time, right? In this case, we want to usually use the units hertz, and that's what the answer is there. It's 3.3 hertz. Hertz just means cycles per second. So we always want to have seconds as our time. So 200 cycles, and the time is 1 minute, so 60 seconds. So our frequency ends up being, if we do the calculation, 3.3 hertz, or 3.3 cycles per second. So every second, the speaker goes back and forth 3.3 times. You would not be able to hear this. Human hearing basically starts around 20 hertz. So this is too low of a frequency for us to ever hear. Second, it asks for the period. And if you remember what the period is, it's just the the reciprocal of the frequency. And period, we use the symbol T. And instead of cycles per time, it's the time per cycle. So we can calculate it just by doing the reciprocal of this equation. Instead of number of cycles per time, time per cycles. So if it's 1 minute, so 60 seconds, and it is 200 cycles, that means each cycle takes 60 divided by 200, which is 0.3 seconds. Okay, so that's the period. That's how long one of those cycles takes. These two things are inverses of each other. Sorry, I shouldn't say inverse. I should say reciprocals of each other. So we can actually, just to get from here to here, what you could do is you could actually just divide 1 divided by 3.3. Would also get you the period. And to go backwards is just the other way. You do 1 divided by 0.3 to get the frequency. They are inversely related to each other. So looking at this question, we're asked to label the amplitude, wavelength, and equilibrium point of the wave. Remember what the amplitude is. It's the distance from the equilibrium point to a peak or a trough. Remember what the equilibrium point is? It's just that natural resting point of the wave. So let's picture this as a wave on the top of water or something like that. If there was no disturbance, the water would be at this level, and that is our equilibrium point. It's like the center point. Okay? Equilibrium point. So it's that line there that runs down the center. The amplitude, remember, is the distance to that, from the equilibrium point to the crest or trough. So I'll label that with an A for amplitude. Notice how it's going to be the same amplitude down here to the trough. Okay? So that is the amplitude. What else are we asked to find? The wavelength. We're not given any numbers here, but a wavelength, remember, is like from the start to the end of a wave, of one cycle of the wave. So use a different color here. Let's use green. So the beginning of the wave, let's just start with the peaks. Let's go from peak to peak. So if I start the wave here and I go through one whole cycle, so I go down to the bottom and back up to the top, that whole cycle is one wavelength. So that's I'm going to call that one wavelength. And the symbol we use for that is a lambda, right? Sort of like a backwards H-ish. Okay, so that's one wavelength. Notice how we also could have measured the wavelength from the trough, so between this point and the point over here. Or we could have gone from the beginning here, up, down, and back up to this point here. That also would have been one wavelength. What else are we asked to find? Wavelength, equilibrium point, and amplitude. Okay, so we labeled all those things in part A. Part B asks us to list all points that are in phase with each other. What this means is points that occur in the same place, but on one cycle later. So for example, X, if we wanted to find a point in phase with X, we could just travel one cycle, so up, down, and back up again. And if there was a point here, that would be in phase with X. There's not, though, so that isn't a pair of points. Let's try B. So B is like just before the crest. If we followed B for one cycle, so up to the top, down to the bottom, and almost all the way up to the top, we have F. So B and F are in phase with each other. They are one wavelength apart from each other. So we could say B and F, go back to blue here, B and F are in phase with each other because they're a wavelength apart. What else is a wavelength apart? Well, if we look down here at A and go, so it's just below the equilibrium point, we go up, down, and back up just below the equilibrium point, it looks like A and E are one wavelength apart as well. Any other ones? Is there anything in phase with C? Well, if we look at C, C is just after the crest. So if we go down, up, and back up just after the crest, doesn't look like there's a point there. G is close, but not exactly. So I think those are all the pairs that we have, because D we can't go because it's off the edge of the graph. If there was a point like over here, that would be close to D. Okay, but I think B and F and A and E are the ones that are in phase with each other. You can try this one at home, find your hearing range. So you can just go for an online tone generator, just search for tone generator in Google, and you could tell, it'll tell you, like, you can basically just scroll back and forth, and you can see what's the lowest frequency you can hear and what's the highest frequency you can hear. Unfortunately, you probably can't hear the lowest frequency on your speakers on your computer unless you have very large speakers, because to produce very low frequencies, you need to have basically a very large speaker. So you might not be able to test the lowest frequency, but you probably can test the highest frequency. Make sure not to have the volume too high. Turn down the volume so you don't damage your hearing or damage your speakers when you're doing that. And for this last question, it's just asking you to measure the following. So literally, find a ruler, take out a ruler, and measure these things in centimeters. So for example, how many waves are there in the wave train? Oh, that first question is, how many total waves are there? Well, one wave, that's one wave, right? It starts down here, goes up, down, and back up to its starting point. So how many of those are there in this? Well, if you count, we have one wave here, 2, 3, 4, and 5. So the whole wave train, it's called a wave train, just a bunch of waves. There are 5 of them here. One wavelength is what you're looking for here, not the wavelength of the whole thing. We just want one wavelength because that's what the wavelength is. So a wavelength will be from the beginning to the end of this wave. So you can actually take a ruler, measure how many centimeters that is. Same thing with the amplitude. Remember, the amplitude is the distance from the equilibrium point to a peak or to a trough. And you can measure in centimeters what that actually is for this wave. Then you can try those next 2 questions as well in a similar way.